Hello and welcome to Alpha Omega training videos. In this project, we are going to simulate a Mist Eliminator device and then extract the graphical results using ANSYS Fluent software. Stay with us. To start the simulation, open your ANSYS Fluent from the Start menu, and after the Fluent launcher window is visible here, you'll have some options to modify. The dimension of our geometry is 3D. Also the solver options, here we have the double precision. This option in ANSYS Fluent software is a computational setting that allows for more accurate numerical calculations. This option uses 64 bits to represent numbers compared to the 32 bits used in single precision. The double precision effectively doubles the number of significant figures in the calculations, leading to more accurate results. Also, under the parallel local machine, we have the solver processes. This option is a feature that allows you to control the number of processes used for the solver. 2 is enough for my hardware. And also, to import the mesh file, here I select the read mesh. And this is my mesh file. Okay, my mesh file is selected, and now I hit the start. After a few moments, the mesh file is loaded into the ANSYS Fluent, and here you can see the work done in the console. Okay, in order to look at the geometry, there you can select the display mesh option here, or the display button here, or in the domain tab, the display button. Under the options, make sure that the faces is enabled, and here select all the surfaces available in this tab, and then hit the display. You can rotate, zoom in, zoom out, or move your geometry using your mouse. Also, I can deselect some of my boundaries, for example, device walls. So I can see the inner parts of my geometry. Also, by increasing the transparency value, the inner parts will be visible. Also, to check the elements of the mesh file, I again open the display mesh, and under the options I enable the other option, which is edges. After displaying, I can see all the surface elements of my project. As it can be seen, the mesh type is tetrahedra. The elements are generated in the ANSYS machine software. To check the number of the elements, here from the info and size, and here in the console under the cells, we can see that we have near 7 million of elements. And also we can check the mesh file in order to avoid the negative volume for our elements. Also in the report quality, we can check the quality of the mesh file. Here in the console, you can see that we have the minimum orthogonal quality and also the maximum aspect ratio. The orthogonal quality in ANSYS Fluent is a measure of the cell's deviation from a perfect shape. The range is 0 to 1, where 1 represents a perfect cell. Lower values indicate poor quality, potentially leading to increased results. It's crucial to maintain high orthogonal quality, preferably above 0.1, to ensure accurate and reliable simulations. Also, the aspect ratio in ANSYS Fluent refers to the ratio of the longest edge to the shortest edge in a cell. It's an important metric for mesh quality. Fluent can handle high aspect ratio cells, but for better accuracy, it's recommended to keep it below 200. However, in boundary layers, it can be several thousands. Okay, I want to now change the type of my elements from tetrahedral to polyhedra by just clicking on the option Make Polyhedra. This will decrease the total number of elements, and also it will increase the quality of my mesh file. Okay, after a few minutes, the polyhedron mesh type is generated. If you zoom in, you can see the tetrahedra type, but in order to update the elements, open the mesh display window again and hit the display, and that's it. This is the polyhedra mesh type. Now I check the quality of the elements. That, as you can see, the quality is increased. Also, the total number of cells have decreased to about 2 million, which is great for our solution. You can also increase the quality of elements using quality option and improve mesh quality. Here I enter the 0.2 for the percentage of cells to be improved, and 5 iterations and improve. Okay, it is done. I close the improve mesh window to report the quality again. You can see that the minimum orthogonal quality is increased to 0.22, and also the maximum aspect ratio is approximately 24. To continue, here under the solver we have some options, which the first one is the type, solver type, which is selected pressure based by default. The pressure based solver in ANSYS Fluent is primarily used for incompressible and mildly compressible flows. This solver uses a pressure correction to solve the Navier-Stokes equations. The steps involved include guessing the pressure field, solving the momentum equations to obtain a velocity field, and then correcting the pressure field based on the divergence of the velocity field. The process is then iterated until a converged solution is found. This solver is efficient and suitable for a wide variety of flow problems. Also, in case of time, the fluid of our project, which is air, is considered to be steady. Also, we have gravity in z direction with the value of minus 9.81. In the next step, which is the models, by double clicking on it, you can see the whole models available in ANSYS Fluent software. The first model we want to modify is the viscose model. By double clicking on it, we can see the different turbulence models. But what I want to select is the two equation K epsilon model, which is realizable. This model offers an improvement over the standard K epsilon model by providing superior performance for flows involving rotation, boundary layers under strong adverse pressure gradients, separation and recirculation. The realizable K epsilon model is based on the transport equations for the turbulence kinetic energy and its dissipation rate. The term realizable means that the model satisfies certain mathematical constraints on the Reynolds stresses consistent with the physics of turbulence. The benefits of using this model include its robustness, economy, and reasonable accuracy for a wide range of turbulent flows. That's it. The next model is Discrete Phase, or DPM. The Discrete Phase Model in ANSYS Fluent is a powerful tool used to simulate the flow of discrete particles or droplets in a continuous phase. It's particularly useful in multi-phase flow simulations like particle tracking. Here in this project, we consider that the water is particle which enters with air from the inlet boundary condition. In the Discrete Phase Model window, the first option is interaction with continuous phase. The interaction with continuous phase option is a setting that allows users to model the interaction between the primary phase and the secondary phase. This interaction can be in the form of drag, lift, virtual mass, wall lubrication, and turbulent dissipation forces. Also, we have the update DPM sources every flow iteration. When this option is enabled, the source of mass, momentum, and energy from the discrete phase to the continuous phase are updated after each flow iteration instead of after a complete DPM iteration. This can potentially lead to a more accurate solution, especially in cases where the interaction between the phases is strong. However, it may also increase the computational cost. Here we have the DPM iteration interval. The DPM iteration interval is a parameter that determines the frequency of particle tracking calculations in a discrete phase model simulation. If you set the DPM iteration interval to n, Fluent will perform particle tracking after every n flow iterations. This means if you have a high iteration interval, the particle tracking will be less frequent, which might speed up the simulation, but at the cost of accuracy. On the other hand, a low iteration interval will result in more frequent particle tracking, leading to a potentially more accurate but slower simulation. It's a balance between accuracy and computational efficiency. Here the 10 is enough for our solution. In the tracking tab, here we have the max number of steps, which is set to 50,000. The max number of steps is used to set a limit on the number of steps that a tracked particle can take. This parameter is particularly useful in controlling the computational time and resources. If a particle's trajectory is complex and requires many steps to compute, it may consume a significant amount of computational resources. By setting a maximum number of steps, you can ensure that the computation completes within a reasonable time, albeit at the risk of truncating the particle's path if it requires more steps than the specified limit. Here the step length factor is a crucial factor that determines the size of the steps taken by the solver when tracking when tracking a particle in the flow field. This particle is a multiplier for the local cell size, and it's used to calculate the maximum allowable step for a particle. A smaller value results in smaller steps and potentially more accurate tracking, but at the cost of increased computational effort. Conversely, a larger value may lead to faster calculations, but with a risk of decreased accuracy. Here the option high-res tracking is enabled by default, and it's a feature that enhances the accuracy of particle tracking. It does this by using a second-order numerical scheme which reduces the numerical diffusion that can occur in the tracking of particles. This option is particularly useful when dealing with complex geometries and flows like our project. Also in our solution, the motion of particles is considered to be unsteady. The particle time step size is 0.001, while the number of time steps is 10. At the next step, I want to define the injection of the simulation. So in the discrete phase, I double click on the injections, and here in the injections window we can create a new injection. Here in the set injection properties window we can change the injection name. We can select the injection type. Our injection type is surface, which will be injected, particles will be injected from the inlet boundary condition. The injection surface is inlet, its type is inert, the material is water liquid. The diameter distribution is uniform. And also I enable the option inject using face normal direction. The injection will be normal to inlet boundary condition. The diameter is 0.1 millimeter. The start time is 0 while the stop time is set to 15 seconds. Also the velocity magnitude of particles here in the inlet is 0. And the total flow rate is 0.015 kilogram per second. And that's it. Okay. And the injection one is defined. In the next step, which is materials, you can select and modify the properties of different materials that are defined. For example, in our solution, we have air as fluid and water liquid as particles, which will form our mist. By selecting the material and hitting the create edit, you can look at the properties of the materials. For the water liquid, we just have the density. Also in the cell zone conditions, we can allocate our materials to the zone we want to simulate. Here we have one zone, which is the Mist Eliminator. Click on it and hit the edit. And make sure that in front of the material name, the air is selected. The fluid of our domain is air. Next, we need to set the boundary conditions. So you can double click on it. And here you can see all the boundary conditions of the solution. Also, you can classify them by their type by clicking on this option and hitting the zone type. And as you can see, we have one inlet, one interior, one outlet, and 2 wall boundary conditions. Click the inlet and edit. The velocity magnitude for the air is 6.4 meter per second. Also, the discrete phase boundary condition type is set to escape. This boundary condition is suitable for inlet and outlet boundary conditions, which will pass the particles. The next one is interior, which shows our domain, and it's not a boundary condition. Here, as you can see, there's no option to modify. We have the outlet air, which is this boundary condition. In the pressure outlet boundary condition, there is nothing to modify again, but check that the gauge pressure is set to 0 Pascal. And the DPM boundary condition type should be escape. Here we have the device walls. Make sure that the wall motion is set to stationary wall, and also the shear condition is no slip. In the DPM tab, the discrete phase boundary condition type is set to reflect, which shows that this boundary condition will reflect the particles with the same angle they hit this wall. Okay, close it. And the last boundary condition is Mist Eliminator walls. To show you. This is the boundary condition. And we want this boundary condition trap all the particles that hit it. Okay, in the momentum tab, the options are the same as the device walls, but in the DPM, the discrete phase boundary condition type should change to trap. Apply and close. Next in the solution, we have the methods tab. Here we have solution methods, which the first is pressure velocity coupling. The coupled scheme is set as default for the pressure velocity coupling. In the coupled scheme, the velocity and pressure equations are solved simultaneously using a matrix solver. The matrix solver takes into account the full coupling between the velocity and pressure fields and iteratively solve the equations until a converged solution is obtained. It's important to note that this scheme can be computationally expensive. Also, in the spatial discretization tab, we have the gradient, which is set to least squares cell-based. Least squares cell-based, also known as LSC, is a cell-based approach for calculating gradients that uses a least squares fit to estimate the gradients across a cell. The LSC method is particularly useful for simulations with non-uniform mesh sizes or for cases where the cell aspect ratio is high. Here I put pressure to Presto. The Presto is a method that provides accurate and stable solutions for a wide range of flow problems, including those with complex geometry. Also, it's computationally efficient, allowing for faster simulations and reduced computational cost. Presto can handle both laminar and turbulent flows with ease, making it a versatile option for engineers. The momentum is second order upwind, and also the discretization for turbulent equations are first order upwind. Here we have the warped phase gradient correction option. This option is a technique to correct the gradient values of a solution on distorted or non-orthogonality mesh faces. This technique is used to improve the accuracy of solution by ensuring that the values are consistent across all mesh faces, even those that are distorted or non-orthogonal. Then we have Controls tab, in which the relaxation factors can be modified. The under relaxation factors refers to the numerical parameters that control the rate at which the solution variables are updated during each iteration of the solver. These factors are used to improve the stability and convergence of the solution by controlling how much each variable is allowed to change from one iteration to the next. In the report definitions, we can define some reports from the solution. For example, if you right click on the report definitions, new and surface report. For example, the area weighted average. You can report the velocity of air on the outlet air. Using these settings. And also it will print to console. You can also select other parameters available in the field variables. In the monitors, we have residuals. Residuals are the errors that remain after each iteration of the solution process. The goal is to minimize these residuals to achieve a converged solution. Make sure that the plot and print to console options are enabled. And here we can see the absolute criteria of each equation. The initialization refers to the process of setting up the initial conditions for simulation. The purpose of initialization is to provide a starting point for the simulation that is consistent with physical conditions being modeled. This allows the simulation to converge more quickly and accurately towards a solution. I select the hybrid initialization and initialize. This will solve the Laplacian equations for the project in 10 iterations. Okay, the hybrid initialization is done. And now we can go to run calculation. And change the time scale factor. Decreasing this value will improve the convergence of the solution. And also the number of iterations will be 15,000 that will perform the solution until 15 seconds. Okay, the solution is ready to calculate, but before that, I want to define a view in order to save every, for example, 60 iterations or time steps, and after that, the ANSYS Fluent will give us an animation file from the particle tracking. So to do that, I can open the calculation activities, double click on it. Here in the autosave every iterations, enter the, for example, 500. After every 500 iterations, case and data of the solution will be saved. After that, to define the animation view, we need to define a graphical view. So here, open the graphics under the results. Double click on the mesh. And here select all the surfaces except the Mist Eliminator walls.
How's Dickens? Did somebody comment?
I just selected device walls, save and display, and this is the geometry. This is the first mesh. Again, double click on the mesh, and now select other boundaries and save display. Next, in the particle tracks, I select the injection 0. Here I increase the skip value in order to decrease the number of particles. And here under the color bar you can select the parameter you want your particles to be colored with. The particle residence time is a suitable parameter for me, so I hit the save display.
Actual one. Continue.
Okay, that's it. Because we have no particles yet, we can see nothing. And then I go to scene, double click on it, and here I enable both the mesh I defined and also the particle tracks. Here I increase the transparency of the mesh 1 and save display. Okay, that's it. Now we can see both the geometries and the particle tracks. Again, I go back to the calculation activities, I open it, and in the solution animations, I double click on it. I want every 60 iterations, my scene gets saved, and this view is a suitable view. And now I hit the use active view, and the view 0 will be defined. Okay, and it's done. After that, go back to the run calculation and hit the calculation. The solution will start to be calculated, and after a few seconds you can see the residuals tab here that will show you the residuals of every equation. Finally, the simulation is completed and I stop the calculation after more than 10,000 iterations. Here you can see the residual of different equations available here in the residual window. Also in the scene 1 tab, you can see the animation of the view we have defined in the calculation activities. Okay, we can see also the contours or vectors of the solution. But first we need to define a plane in the XZ plane. So here in the create plane, the method will be ZX, which is at the center of the geometry, with the name of ZX and create. Okay, the pressure of the domain in the ZX plane is like this. Also the velocity. This is the velocity of air. And different other parameters, which could be the turbulent intensity. Here I double click on the vectors. the vectors of velocity, which is colored by the velocity magnitude. I disable all the surfaces, and here I select the ZX plane. I can rescale it with a value of 3, and this is a much better view. Also, to extract the streamlines, you can double click on the path lines. Real from surfaces. I select the inlet. To decrease the number of streamlines, I increase the path escape and color by the velocity. Save and display. And these are the streamlines. We can also look at the streamlines and geometry at the same time by disabling the particle tracks and enabling pathline. And the grid view. We can also save the scene by clicking on the save picture, choosing the format, the white background, and disable the use window resolution and select the resolution you want, for example 4K, and hit the save, and the picture will be saved. And now we have a high quality figure of streamlines. And finally, this is the animation of the solution until 15 seconds. Okay, that's it. The project is done successfully. I hope that you have enjoyed this project.